Hello everybody! So, as many of you probably already know, the James Webb Space Telescope has been hit by a larger than expected micrometeoroid. Nonetheless, the telescope didn't suffer any significant damage that would drastically reduce its performance, which continues to be still well above expectations, and scientists are still targeting July the 12th to finally release the first official images, for which I have really high expectations, especially after having seen these ones. Now the question is, after having suffered its first relevant impact, how many more can Webb handle before it's rendered useless? Well, micrometeoroid strikes are an unavoidable aspect of operating any spacecraft, and so Webb was of course designed with this in mind. Its mirror was engineered to withstand a steady bombardment from the dust particle environment present at the second Lagrange point. This was accomplished by performing a mixture of simulations and actual test impacts on the mirror samples that eventually helped create a more fortified space telescope. Now, since launch, there have been 4 smaller measurable micrometeoroid strikes, but only the latest one was larger than initially modeled and beyond what the team could have tested on the ground. It actually affected segment C3, not too much, but still enough so that the engineers had to make a small position adjustment of that segment to minimize the effect of the impact. So, how many strikes Webb will be able to handle will really depend, I think, mostly on the size of the particle as well as the frequency with which these impacts happen. If most impacts are coming from really tiny micrometeoroids, then the observatory will be able to preserve its capabilities for a much longer period of time than if it was constantly hit by larger dust particles or really potent cosmic rays coming from other exotic places in the galaxy. Now, in terms of the amount of meteoroid impacts, the second Lagrange point isn't the worst place for Webb to be in. It has a known dust particle environment, but it could be a lot worse. 2 good examples of this are the Parker Solar Probe, which has to deal with a lot more hypervelocity impacts from interplanetary dust particles that are more concentrated on the vicinity of the Sun, or the Hubble telescope, which has to deal with a huge amount of pollution in Earth's orbit that contains many objects of human origin, such as satellite debris. Now, if we take a look at this pollution simulation in lower Earth orbit, this is what Hubble has to put up with. And in this picture, you can see a section of a solar panel from Hubble that was brought back to Earth after its repair mission in 1993. The panel had sustained hundreds of impacts, ranging from microns to millimeters in diameter, after only 2 years in space. Now imagine the 10 million Webb telescope orbiting in this mess. I mean, of course, pollution in low Earth orbit is a problem that we have to deal with, but luckily the Webb telescope is in a much safer environment. Now, also luckily, the James Webb Space Telescope was designed with performance margins to be able to carry out its science missions even after many years in space, and also a couple of tricks up its sleeve to better handle certain spooky situations. For example, Webb's optics were kept cleaner than required during its time on the ground, thus improving overall reflectivity and sensitivity. The telescope is also capable of sensing and adjusting the position of its mirrors, which helps to make partial corrections in case of having suffered an impact, and this is exactly what has been done with the already slightly damaged segment C3 after the latest impact, although of course not all of the degradation will be able to be cancelled out this way. It's also worth mentioning that the damage on the C3 segment will not have any impact on the performance of the near-infrared camera, because this particular segment is overlapped by a secondary mirror strut, as is the case with other 3 segments, and the light coming from these overlapped segments is actually blocked by a so-called Lyot stop, which is an optical element designed to limit which light rays pass through an optical instrument, such as a telescope or camera, so as to remove diffracted rings of light from a bright object, which could be a star, within a coronagraphy. So at least for the near cam, this particular impact won't be as relevant. Another trick that Webb's flight teams can pull off consists in using protective maneuvers that intentionally turn the optics away from known meteor showers if they are able to detect or predict them beforehand. This most recent hit was not the result of a meteor shower, but rather an unavoidable chance event. There are many more such impacts expected to occur during its lifetime. It's sad and it is what it is, but the good thing is that these impacts will help improve the knowledge about this dust particle environment at the second Lagrange point, and in turn that will be really useful not only for this mission but also for future missions as well. And with that, I finished this video. I hope you found it helpful and informative. I'm really looking forward to the release of the first images on July the 12th, and I think it's gonna be great. If you like, I will see you again soon in the next one. So until then, have a nice day, take care, bye bye.